session. The plan for today looks like this. I spent 30-40 minutes summarizing the course. I then again spent a few minutes giving an overview of the entire course in a single slide from a different perspective. Then the second part will be just a few minutes on your evaluations, a few more minutes on other courses that you might want to go ahead and take after this one, and finally some exam information and looking, to the extent that we have the time, at a few of the specific questions, exercises from the exam from last summer, from this summer. Please note that just after the break today, during this double lecture, I will decide at which time there will be a question session, 90 minutes with me. It is impossible to find a time where everyone can, so it's an extra service for the most of you, and then we will record it. I will record it, so the rest of you who might have an exam or anything, something else important, you can take it online. Yes, that's the plan for today. Let's get started. A course summary. I'll do it in a way in 3 steps, in 3 parts. I'll sort of do the first part, you could call that a bit of basic stuff. Then I do sort of the basic stats, you could say basic stats, really basic stats, and then sort of Rolls-Royce. How do I spell Royce? Like that? Rolls-Royce stats. At least the cheapest version of the Rolls-Royces. There are better and bigger Rolls-Royces out there, but you get to see a flavor of it in this course, right? So that's the plan for this. Let's get started. The first thing I bored you with 13 weeks ago from chapter 2 was how we could start out by looking at data as they are. That was chapter 2 in the book. Here is some data. This course is about data. Of course, we should still look at the data like we started in 3rd or 2nd grade. We shouldn't stop doing that. We should use the tools we have already seen, and we should maybe even develop new tools. We should look at data by plotting. We should compute maybe summary statistics to tell sort of a summary story of the data we have, and we have met the mean and the standard deviation and variance as an important thing to tell the story about variability. We saw other ways of summarizing data in the beginning. We saw the median and upper and lower quartile, sort of a more robust way to sort of tell the story about data, like saying this is the point in the middle of the data, having 50% to the left and 50% to the right. That's the median. That could be generalized to saying here is a point that this is, I have 80% below me and 20% above me, so I'm an 80% percentile, you could say. And then, of course, we should still do basic graphics. We have some tools for that. If you like, use Excel. I use R. Other people use other tools. That's how it is. Then, that was the data. Everything in this course is about data. I said we are going to learn to be intelligent about looking at data. Not just doing this. We shouldn't stop doing this. We should just add a bit of intelligence to what we are doing. Not just looking at the data, but thinking about how can we really use the data and what is the limitations of our use of the data, none the least. To do that, we need probability. And that's the whole key of it. We need probability to look at data in an intelligent way. To become statisticians, to do statistics, we need probability. We are not going to be probability theory people, really. but we need the probability theory at a certain level to be able to be intelligent about it. Probability comes in some general concepts, and then we split it in two, sort of the discrete world and the continuous world, to be exact about it. That's a mathematical distinction. In the discrete world, there are some general concepts of probability. What is a random variable or stochastic variable? We can describe a random variable or the distribution of it by either the density function, showing the sort of the pointwise probabilities, or the distribution function, which is the accumulated density function, right, in the discrete world. And we met 3 specific discrete distributions that we can use for different things around out in the world. Not for everything, definitely, but these are 3 important starts of being able to sort of use probability modeling, probability systems for learning about and doing intelligent decisions, whether we are going to make recommendations for the future population and make sure that we survive even though we have bacteria spreads, or we are going to do cool business out there in the financial area or in the production area. Doesn't really matter. We need to be able to do this intelligently. We could do it by the binomial when we have the coin tossing situation. We could do it by the hypergeometric when we are sampling without replacement. That is, we take a handful at the same time. Then we have the hypergeometric in play, and we had the Poisson distribution that was counting events typically during time or during, you could say, space. That is the typical thing that matches the Poisson distribution. So, and we had the formulas for those, and we could play around with those. We could do probability calculations using those specific distributions. A similar exercise we did in the continuous world, like modeling, where we actually measure something quantitative, the content of alcohol in your blood after the Christmas lunch or whatever, the weight, the height. We are measuring something quantitative. Again, we have some general concept in the continuous world. Density and distribution function as the generic sort of functions giving name to the probabilities, or you should be more exact here, the probability intensity, if you want. We could also deal with mean and variance considerations in general probability models. And we had some calculation rules for those. Remember my airline and ship examples where we were adding up something, and we could use some computation rules for mean, and especially the variance rule was important to get the right version to make the right conclusions. Then we made some specific continuous distributions, the log normal, the uniform, the exponential, and not the least, of course, got its own bullet point here, the normal distribution, which appears to be a very important distribution due to some core results out there in nature. This is not something we have decided. This is nature that has sort of produced this for us, that the normal becomes a central distribution in this context. And then in the chapter 5, we learned, you could say, the first, I call it here, data method, really at least linked to the probability thing. We learned that we could plot the data to see whether it actually looks as if it comes from a normal distribution. We had this QQ plot such that we could check whether data, if you took some real data, you could make a plot and see if it's on a line, at least almost. There's always some random noise in this system. If it's almost on a line, it means that it matches something from a normal. If it's definitely not on a line, the data is not coming from a normal distribution. So it's a way to go ahead and check, given that you have some data in your Excel sheet. Does this really come from a normal or not? It could be difficult to answer. I can go check. I could make this plot and see whether it looks okay. That's important because many of the tools that we're going to present, the classical statistical tools that I present to you, is based on an assumption of normality, at least if we have small samples. We'll get back to that. This was the first part, the basic part. Then we jump to the, you could call it, basic stats part. Starting out with chapter 6, which we did not give its own lecture, sort of. We used the part of chapter 6 during the next couple of lectures, but here, chapter 6 was sort of put forward to its own slide here, because chapter 6 is really important. Chapter 6 is sort of the link between data and probability. To make this is where we are giving the way, the concept of doing intelligent data looking, to be a bit naive, to really do the inferential statistics, which this course is all about. The so-called sampling distributions, this concept and the way of thinking coming there is crucial to everything, really, at least to the understanding of everything. I mean, you may be able to use the tools that I present to you in the rest of the course in a way that's fine. But for the understanding of why this makes good sense, what I'm teaching you, then this chapter is really important. Because this is where we, again, think about sort of the framework that we are facing. We have this population and random sample. This is the way we think. We have this, the population is the unknown truth. It's the unknown world out there. Then we take a subset of the world, the sample, because we have only finite time and money. So we cannot observe the entire world for infinity. That's not possible. So we observe a selection of the world, the sample. We take a subset and look at some data. And then we try to infer about the big and true and key world out there from this sample. This is called statistical inference. The sampling distribution was the way of thinking that when we have one such sample consisting of maybe 20 observations, that's one sample, then the way we should be intelligent about looking at the results of this, because of course we should look at it, using the tools that I just presented you from the beginning. Look at the data, fine. Step 1. Step 2, think. And this is the thinking part I'm getting into here. Think that this one sample of 20 observations is not the ultimate truth. I mean, it's not that difficult to have a feeling of the important part here. It's not that difficult to realize that if I redo this sample tomorrow, then I do not expect to get exactly the same result. I think most of us would already know that before getting into my course here. So in that sense, I'm just sort of taking up something which I'm sure everyone would think about. How much can I really believe this sample of 20? Since I know when I do it again tomorrow, I'll get a different result, and this is my intelligence about it. Yeah, that's good enough, but how can I operationalize this? Or what can I do here? I can try to think about how can this sample of 20 be different from sample to sample. If I know that, and that is random, this is where probability comes in. This is random. So we cannot just say this is the truth and that's it. We can start speculating. What would the distribution be of whatever I compute if I redo it again and again and again and again? What is the sampling distribution of whatever I compute? This is a generic way of thinking through the entire course. If I know this sampling distribution, I know everything to the extent that I can know everything, because I cannot get around the randomness part of it. It is random, nothing to do about it. But if I know how it is random, I'm the intelligent guy. So if I know the sampling distribution, I can be intelligent about it. I can do statistics. I can make the right conclusion under the risks that I know that are there. It's not that the risks are gone, but I know what they are, and that's a hell of a difference if I make decisions based on known risks rather based on nothing, right? So that's the intelligence part of it. That's the sampling distribution. We also learned the central limit theorem back there. The central limit theorem that tells us that when we average things, then they become normal. That's the short version of it. When we average things, then the way such average things behave from sample to sample becomes like a normal. And the bigger the n, the more like a normal. It's a key result. The more we average, the more sampling distributions becomes normal. So this is a core result. Everything is about sample distributions in statistics. Central limit theorem provides an approximate sampling distribution for basically everything. Everything becomes a normal finally, and that's the crux here. That's the challenge here, that it may not work in all relevant cases. It may not work for small n. So it's not that we can use the normal for everything. However, we met 3 specific sampling distributions there. We met the normal that can be used, as I've said, sometimes as the sampling distribution due to central limit theorem, or if we know the variance, or there are certain situations where the normal may be used as the sampling, or other sampling distributions often used as the t distribution, the chi-square distribution, and the f distribution. Theoretically, these are sort of comes from the normal. If something is normal and you divide it by a computed variance, it becomes a t. If something is normal and you square it, it becomes a chi-square. If 2 things are normal, you square them and you divide them by each other, they become f. That's probability theory, not in our course, but you could learn that in a probability course if you wanted to. Or check some of my additional math lectures. I'll not give sort of thorough proofs, and the sound is a bit bad there. I'll fix that next year. But you can look at it at least. Let's go to the specific tools now of the basic stats. The specific tools of the basic stats part here. 1 and 2 samples, looking at means. 1 average or 2 averages. Very simple-minded, you could say. Again, this is where we were really taught how to do statistics. Using the ideas, the sampling distribution ideas coming from chapter 6, but in chapter 7 and 8, we became specific. Here's how to do it, and here's how to think in specific cases. We can estimate things with confidence intervals, and we can do hypothesis tests. With hypothesis tests comes p-values, type 1 and 2 errors. We didn't spend so much time on the type 1 error. The type 2 error. The type 1 error is the one we always control. That's the risk that we know we are doing. And there are 2 things we do. We do confidence intervals and we do hypothesis tests. That's our tools of doing the part, the statistics, the intelligent part. That's the operational tools we have, and we should learn to use them. You should have learned that now, and it's very good if you also have a feeling of the meaning of everything linked to the sampling distribution, of course. The more you understand, the better you're off the rest of your life. I'm not saying you have to understand 100% to pass the course, but the more you understand, the better for you. And for our country in the future. We learned specific methods, 1 sample, test and confidence interval for the mean, like a t-test, and we could also calculate the sample size. We could turn this formula around for the confidence for the maximal error, and then we had sort of a formula for n. And we had some specific methods for 2 independent samples and also 2 paired samples. We could do test and confidence interval for the difference of 2, and we could, for the paired sample, if we have 2 that are sort of before, after on the same individuals, like that, we could, basically we take the difference and we are back into 1 sample. So in a way that's, even though it has its own name, in a way it's an easy thing to do. As part of the basic stats still, we also learned in the same situations that I was just talking about where we computed means, we also learned that we could sometimes focus on the variances in either 1 or 2 samples. Specific methods are the following. So this is the heading. For 1 and 2 samples, we could do confidence interval for 1 variance based on the chi-square. This is something from the book. We could also do a hypothesis test. Could a variance be equal to 8, for instance? This is my hypothesis. I could base that by simply taking the variance in relation to the hypothesized values, and out came a chi-square statistics to do such a hypothesis test. And we could compare two variances. This became a chi-square, and this became an f-test, where we compare two variances with each other, and an f-test appeared, and we could use that to make a decision. Is the hypothesis acceptable or is it rejectable? That's how we do hypothesis test. Remember that, right? I didn't repeat that because I've repeated that in every lecture, how we do hypothesis test. The final part of this sort of basic stats was, in a way, how do we do basic stats on proportions? That is, when we basically measure a binary thing, we ask people to vote for this or that, or we flip a coin, or do you survive a disease during a medical study, or did you improve, or we count something. That's the proportions situation in chapter 10. We learned some specific methods for 1, 2, or actually more than 2 samples for the first time in this categorical setting. We could estimate proportions, including confidence interval. We could do hypothesis for 1 proportion. We could do hypothesis for 2 proportions. This actually came out as a set test. In fact, the 2 proportion thing was maybe, I think, not quite, but one of the few things in the course where we were given 2 alternatives for the same thing. We were given a set test where you directly compare the 2 proportions with each other and get a set test, and we were given a chi-square test of this 2x2 table. Then we call it a frequency table or a contingency table. And then, because we learned this, the chi-square test for an R by C table of counts. So we could have an arbitrary number of rows, an arbitrary number of columns in such a table of counts. And there is a basic test for, you could call such a test for relationship, if that's the sensible way of interpreting the specific situation. It could also be a test of homogeneity of distributions. It's the same test, actually, and it's just 2 different ways of thinking about those numbers. Are such a table of frequency counts, are they having the same distributions in all the rows? I'm showing columns, so in all the columns. Or do they have the same distribution among all the rows? Or are they related? Actually, this is the same thing, if you think about it. And it leads to this chi-square test where we compared the observed counts in such a table, for instance, the 3x3 table, with the so-called expected counts. So that was the way to do it. We should compute the expected counts, and then we should compare the expected within the hypothesis with the observed, and we combine all of those into a chi-square statistic, and that was the test we were taught there to do this. And this is a copy-paste error from previous. We didn't do this in this course. We did other nice stuff in our course. This was basic stats. This was the second part of my recap of my summary.